Today we will be talking about the, oh my goodness, sliding filament mechanism, which is how your muscles contract. So when your body's sensory neurons receive input that is sent up to the CNS, or the central nervous system, and it sends the signal back out through the motor neurons to effectors like muscles and glands. Those muscles and glands may contract or they may relax, but we're going to be talking about how it contracts using this sliding filament mechanism. We're talking about skeletal muscle right now. Smooth muscles contract in a little bit of a different way. They have intercalculated discs between them and they're diamond shaped. So the effectors will release, the neurons will release acetylcholine into the stream. They release acetylcholine into the synapse, and acetylcholine is the most common neurotransmitter, and acetylcholine will trigger the production of calcium. The calcium stores in the ligand-gated ion channels, and that will be flooded into the sarcoplasmic reticulum. It's like, now what is the sarcoplasmic reticulum? Well, in the muscle cells called muscle fibers, there are myofibrils, which are surrounded by a fluid-filled sarcoplasmic reticulum. And within that reticulum is a bunch of myofilaments, which are very, very tiny. And that's what we're going to be talking about. That is the smallest layer, and that is where the contraction happens. So, what does a sarcomere look like? A sarcomere, I'm doing it on this side, so it's not, well, I'm going to do it on this side. That's your Z line. You can see why it's called a Z line. Looks like a ticket stub. That's the M line, M for middle, easy to remember. That is super uneven, ignore that. And in the middle you have these thick filaments, thick myofilaments. And then at the end, from the Z disc, you have these thin filaments. And they overlap a little, not a lot. From either end they come. Now, this here, that's only thick filaments, that's called the H zone. This here, where it's only thin filaments, that's called the I band. Of course, the M line, the Z disc, which separates sarcomeres. They're like this. This would be another sarcomere. You see? And the M line, which is, of course, the middle. There are a couple of other divisions, like the part that's only thin filament, but we're not getting into that right now. So, let's zoom in on this, but first, what happens when this contracts? Because this is what is contracting. Well, it starts to look, we're going to do same scale here, more like this. It starts to look much shorter, and the lines almost completely overlap because they're getting closer. The filaments are sliding together, and the I band will become much smaller. The sarcomere is capable of contracting up to 70% of its resting state, and this is what that's called, the resting state, where nothing's happening. So we know that there's calcium and that's triggering something, but how? How is that triggering anything? So we're zooming in again. The M line. And then the thick filaments. It's all these little golf club looking boys. And these are called myosin. And they don't look exactly like this, but they look like golf clubs. And they come on either side. You'll notice that these look a lot worse. It's fine. And the myosin, we're going to label that myosin, they have two active binding sites. They have one active binding site for actin. What's actin? Actin is the thin filaments that aren't quite overlapping yet. And they're completely different. They're like all twisted together. I'm using that as a baseline to draw my now the thing, and it's on either side. The thing about actin and myosin, these two myofilaments, because that's what they both are, is that they love each other is the best way to describe it. They want to be near each other, they want to connect. But there is something that is preventing them. This thing is called troponin and tropomyosin, and it's bound onto the actin, and it blocks the myosin. So the myosin really wants to touch and get to know the actin, but it can't because of the troponin and the tropomyosin. These troponin, let's write that out. Troponin, I really need to learn how to spell these things. Tropomyosin. These are regulatory proteins. And so another thing, I already said that myosin has two binding sites. So we know that one binding site is to actin. What's the other one? Well, the other one is for ATP. And we're going to draw a little ATP in black. Adenosine triphosphate. ATP. And you probably already know about this. This is the main currency of everything. It's the main currency of everything. But how it does that is it transforms itself through, well, it doesn't transform itself. It is storing energy right now. And things that want to use it for energy use hydrolysis, which is the action of putting water into something. There's also a dehydration reaction, which is taking the water out, but producing water, so it's kind of a little confusing. But you put water in, however you may do that. Myosin does it with an enzyme, and that ATP becomes ADP, or adenosine diphosphate. One of those, so triphosphate, adenosine triphosphate means 3 phosphate groups. Well, they lose one. Now it becomes adenosine diphosphate and a phosphate group. That is what this myosin does. Why didn't I label the actin? I would probably not forget its name so often if I just labeled it actin. Anyway, so the myosin will have the ATP bound to it. And we're not going to draw all that because that would be extremely tedious. But it has all that bound to it. And that is where it's getting the contractile energy from. But it can't contract yet. What are we talking about? Contraction, what are we talking about? Well, that's what the calcium is for. The calcium convinces the troponin and the tropomyosin to go away, to fall off. It binds to it, it takes it away. So let's get a little close-up on this. So you can see that the thick filaments in the middle extend out, and the thin filaments extend from the side. These are the thin, these are the thick. I know it's a little reversed. That's because my drawing sucks. All right. So let's get a little closer so we can see how, like, you can see it here. These look like golf clubs. We're going to go and look at one golf club. Okay, so the troponin and the tropomyosin, they fall off, all right? Here in the long line of golf club heads is one golf club head. Down here is its sweet, lovely actin. It has its little ATP, which it has now transformed from ATP into ADP. Now, doing that hydrolysis reaction has given it a lot of energy. So how is it going to use its energy? Well, it's going to come down from where it is, and it's going to attach to it and perform what is called a power stroke. And this is a little difficult to explain. It's going to take this part and move it this way. Did I draw that wrong? Let me see. Would that be on that side? No, it won't be on that side. No, it won't be on that side. Trust me, we're fine. It's fine. And it's going to pull it to go that way. Let's see. So as it pulls it down, it's going to end up over here, and the whole thread moves. It's all connected, so the whole thread will move. Now, once that energy is spent, because it's not infinite energy, the myosin will detach and fall right off. Because the adenosine also falls off. It's been spent. It's done. And it'll return to a resting position. But now, this was moved from here to here. And now what does that look like? That looks like this. All of them, all of the little golf club heads in the thick filament are doing that all at once. They're pulling it together. And that pulls the thin filaments, which remember, the thin filaments are attached to the Z discs at the end. So what happens when you pull them all together? Everything shortens. The Z discs come closer together. So, well, how many times does this have to happen? Well, a lot, but at full contraction, like I said, it'll be 70% of its resting. It'll be real tight. And it'll keep doing this if it's still supplied with ATP and there's still no troponin or tropomyosin blocking it. It will continue to do this, continue to walk it forward and tighten it. As soon as there is a binder or a lack of ATP for whatever reason, this process will stop and the Z discs will come apart. So that is the sliding filament mechanism. The process of the myosin, touching the troponin and pulling it has been described as it walking, but since the actin is the one that moves, I prefer to think of it like an oar. It's taking, when you go kayaking or whatever, I don't go kayaking, you stick it in the water and you pull it forward, you know what I mean? You're pushing yourself. So, see, that's a terrible analogy, actually. The point is, this here is stationary and this is the one that moves. And they all come together. And that's how the sliding filament mechanism works.